In this video, we're going to look at nuclear fusion. So to begin, we'd like to discuss what's called the stability of the nucleus. And the way that we could determine that is by looking at something called the band of stability. So if we look at our x-axis, which shows us the number of protons, and our y-axis showing us the number of neutrons, when you have the same number of protons and neutrons, meaning you have a 1-to-1 ratio, you are going to be a stable nucleus. So for example, let's say you had an atom that had 20 protons and 20 neutrons, you would be stable. You had 50 protons, 50 neutrons, stable. So let's look here on the graph, see 50 protons and 50 neutrons meets at this point, which is on the line. Since it's on the line, that means it's on the band, so falling within the band of stability, so that would be a stable nucleus. Well, what happens if you had something that had, let's say, 70 protons, but only 30 neutrons? Well, that would be considered unstable, and it would release certain particles to become stable. So let's say you had too few neutrons. Well, then an atom in that situation would probably release an alpha particle. And if you had too many neutrons, a beta particle could be released. So what are nuclear reactions? To understand really what we mean by releasing an alpha particle, releasing a beta particle, that means that something is undergoing some type of nuclear decay, which is a nuclear reaction. And how does that differ from other things that maybe you would have learned about prior to this, like a chemical reaction? So in a chemical reaction, you change or rearrange the bonds, whereas in a nuclear reaction, you're changing the actual nucleus. You're transmutating or changing it into a new element. So for example, here's a chemical reaction on the left. This has methane and oxygen forming carbon dioxide and water. What you just want to note is that I started with a certain number of carbon atoms. This carbon is the black, and on the product side, one black, one carbon. I have 4 oxygen in red. On the left side, I have 4 oxygen in red on the right side. So we're starting with the same number and ending up with the same number of atoms. Whereas in this nuclear reaction, I'm starting with uranium and ending up with plutonium. I'm getting a different element before and after the reaction. So to understand a little bit more about what's happening in these nuclear reactions, we first want to discuss what binding energy is. The particles in the nucleus are called the protons and neutrons, and those together are termed nucleons. The binding energy is the energy that's required to break the nucleus up into those protons and neutrons, or it's sometimes referred to as the energy released when protons and neutrons come together to form a nucleus. We could use an equation to represent how much energy is released or absorbed in this type of reaction. So the binding energy equation is the total energy needed to break apart the nucleus divided by the number of nucleons. And the higher the binding energy per nucleon means that the more stable the nucleus is. So if we look at something like, well, how do we know what is most stable? The highest binding energy is iron 56. So it has the most stable nucleus of any element actually. So we could kind of use that to look at, well, what happens to elements that have binding energies above or below? So elements that are lighter than iron 56 end up undergoing fusion, which means that they start with a heavy nucleus and break apart into something lighter. And elements that are heavier than iron 56 undergo fission, which means that fission is kind of like division, where you have a heavy nucleus and it splits up into lighter ones. All right, so let's explain a little bit more about fusion. Fusion means that you take 2 light elements and you combine them to make a heavier one. So here we have 2 isotopes of hydrogen. This is deuterium combining to forming helium. What is deuterium? So deuterium is an isotope of hydrogen. What that means is that hydrogen has different forms, you could say. They all have 1 proton, but they have different numbers of neutrons. So here we have protium, 1 proton, no neutrons. Deuterium, 1 proton, 1 neutron. Tritium, 1 proton, 2 neutrons. So in the previous example, what happened was we had 2 deuterium. So deuterium having a mass of 2 can form something that has a mass that's greater. So here we had helium with a mass of 3. So the mass got greater. We started with something with a mass of 2 and ended up with something with a mass of 3. If we were to look at this in terms of chemical symbols, you could see we have hydrogen with a mass of 2, hydrogen with a mass of 2, forming helium with a mass of 3. And we could also look at the binding energy in this fusion reaction. So we have the binding energy before and after, and the binding energy after it fuses is higher, and that has to do with the fact that so much energy is released during the process of fusion. So why do we care about fusion? So fusion is important as a source of energy. The advantage is that it produces so much energy. 1 gram of deuterium, like we looked at in that example, can produce as much energy as 1 metric ton is coal. There are no greenhouse gases produced in fusion reactions. There's no radioactive waste. And the fuel, which is deuterium in this case, is abundant in substances like seawater. What are some of the disadvantages? Well, the production of deuterium fuel requires large input of energy for things like electrolysis of water. Large amounts of energy are needed to produce these high temperatures for fusion to occur. Hot plasma must be held together long enough for fusion reaction to become self-sustaining. We haven't yet actually developed a fusion generator, which produces more energy than it consumes. And currently there's no working fusion power plants. But the good news is that nuclear fusion does occur at the surface of the sun and provides lots and lots of energy for us on the sun. So here's just a picture showing you fusion happening, hydrogen nuclei fusing to form helium. And fusion, if we think about it, can be regarded as the ultimate source of all of our energy.